Thank you very much, Jake. Well, this is another one where I'm asking you to think ahead. It's outside of your disciplinary area, and to consider all what goes into thinking about the science work and everything else. And I'm here to report about a workshop that was held here at NASA Ames. And what we were, so it fits in really well with this idea of mission concepts and roadmaps and thinking ahead. So we have Mars forward thinking, we have data that can be gotten in the laboratory, we have considerations about communications and robotics. And I get to introduce the notion of planetary protection, which is required by the Outer Space Treaty. However, luckily for you who are working on the moon, it's not a big deal. We've been there with Apollo, and those decisions have been made to reduce the lunar experiences to lower categories of restrictions. So we have decades of mission implementation with planetary protection integrated, and now what we're doing is saying, how does that apply to human missions? We are walking bags of microbes. We have, for every cell in our body, we have as many as 10 microbes that are in and on us. So when we go to Mars, we will be contaminating. At what level do you set it as a harmful contamination? Part of that is harmful to science. We don't want to contaminate the science that we're doing or to interfere with those searches for extraterrestrial life. So right now, we're working on what amounts to a set of principles and guidelines for human missions to Mars. They basically said, keep it clean, keep the Earth clean when you come back, and there's a bunch of different qualitative requirements that have been set. But if NASA and others are starting to think about missions to Mars, how do we turn that into quantitative requirements that they can be used? How do you take that incremental path forward where you develop actual numbers that engineers, designers, and mission planners can use? So what we're doing is taking mission communities, science communities, and other, and building together with all of the work that we've already done on planetary protection and research here. And we had a workshop looking at planetary protection knowledge gaps for human extraterrestrial missions. And what we've come up with, this is the concluding basically, is 25 knowledge gaps that I think all of you here should be aware of, because they're the kinds of things, as you're doing your own disciplinary research, you could be beginning to think about, there's some research on dusts or dissemination of materials that would be useful information to look at for planetary protection. As you're doing your own research, think about, here's an extra funding source if you want to look at it that way. It has relevance to many different missions, regardless of the target and activities. So for those of you who are unfamiliar with it, planetary protection is an international commitment that is rooted in the Outer Space Treaty, which is a United Nations treaty. Over 100 nations have signed it. Article 9 of the treaty stipulates that when we do exploration, it should be done in ways that avoid the harmful contamination of the target body that you're going to, and also adverse changes to Earth when and if you're bringing things back. The facts about planetary protection, there's a lot of misinformation out there, but it applies to both robotic and human missions beyond Earth orbit. It doesn't apply in Earth orbit. We know we've got microbes there. And we're not doing the kind of research that we have to worry about microbial contamination. The planetary protection policy at the international level is revised over time to reflect the latest understanding in science. So there's a lot of attention to microbes, obviously, but there's a lot of information that you all can give as well. Planetary protection policies apply to government and non-governmental entities alike. So anyone who's planning commercial missions needs to be aware of planetary protection. It doesn't stop you. It doesn't put up a red flag. It certainly puts up a yellow flag that says there are considerations you have to go through. And the good news for all of people at this meeting, the moon and most near-Earth objects have no significant operational restrictions, and planetary protection will just fit in. So what we're doing is saying, while we're committed to planetary protection and have all sorts of directives that apply to both outbound and inbound spacecraft, how do you move from what we know about robotic spacecraft and apply it to setting appropriate regulations or controls for human? And previously, we've went to the Apollo sites, and we can talk about the Apollo missions. That was before EPA was ever even established. It's before the technologies have changed. Our science and knowledge about microbes have changed. So anything we did on the moon is a good first place to look, but it isn't anything that is the kind of direct applicability that we would expect now. So currently, NASA requirements are under construction. We're basically saying, how do you bring everybody together to look at how we're going to set these requirements? So the roadmap to human spaceflight requirements is basically something that was started by the NASA Advisory Committee and the Planetary Protection Subcommittee, which said is we can't build on what we have to start to do this stepwise, and that there are some key areas that we know are important. Comprehensively monitoring microbial communities associated with human systems, developing technologies for mitigating or minimizing contamination, and understanding environmental processes that might spread contamination. And so what we're doing is a step forward approach where we took current literature and knowledge and did a big search on that, added it to discussions and deliberations in this workshop, and now we're going forward little by little and calling for more research to address the questions that we have. So there were about 100 attendees, and we framed the entire agenda around these three separate areas: the microbial health monitoring, technology and operations for mitigation of contamination, and natural transport on the body. And so the whole attention to the workshop was to identify the knowledge gaps. Where should we be doing our research in order to address and combine our information about the science and the microbes and planetary protection with what you all are doing, and assess the types of and levels of research that are underway and where those gaps are. So the format was to go through something like here, where we had plenary sessions followed by subgroup sessions and reporting back. And they were, again, designed into the three different areas of human health and microbial. So we had folks from the human side of things and ISS, technology and operations for contamination control. What do we do for science? How can we think about basically avoiding false positives? And what about the Mars environment? If we can show that, for instance, every organism or every fleck of dust that gets outside of a habitat, if it would have a microbe on it, if that's exposed to conditions that would kill any microbe that we know of, then planetary protection goes away. Then you're just talking organic contamination, not the kind of infectious contamination. So we had 5 subgroup questions that all of the groups looked at, and the idea was not to prioritize the questions, that's for NASA to do, but to identify specific research areas that are needed. So I'll go through the 3 areas. In human health and microbial monitoring, sample collection technology and procedures. Big thing. How do you do it? Make sure when you're collecting your science, you do it well. Technology for microbial monitoring. You'll have to monitor all the time. And how will you link that with, for instance, contamination, exposure to particulates of some sort, dusts. Dust is a contaminant for the lungs of an astronaut, so the flight surgeons care about that. Dust is a problem that if a microbe's on it, you can get fouling and corrosion, or dust is a problem that could be a dispersal problem, taking these microbes on dust particles and spreading them around the planet. Now you've got 3 significant areas all looking at dust. Bring all of those experts together. Don't solve it 3 separate times, do it once. Sample processing technology. Will the astronauts even be allowed to handle samples in the labs on Mars? One would hope so, but do you need the same kind of biosafety labs that you do here? Data collection and storage and interpretation, you want to do it there or bring them all back to Earth much, much later. And then you have to look at also the spaceflight microbial responses and changes. What happens to microbes up in space when we know that the human immune system is decreased up there, but microbial factors are often increased. Do we have novel approaches for disinfectants of different sorts that would work up there? Or can we somehow figure out ways to recover from biofouling and biofilms that are a problem for equipment? And are there treatment options that we could have for astronauts? And what are the ethical and operational guidelines that would apply to an astronaut that got sick? Flight surgeons raised that one. We have to think about it in ISS. Technology and operations for contamination control. Does the duration of the surface stay matter? If a 30-day versus a much longer one? Are the microbial problems something that develop much later, or do they come on early in the mission? What level of non-viable bioburden escape is acceptable? So that means if something gets out and it dies, even if it's a spore or something, that's a contaminant, but a contaminant for science. What level do we put that down as an acceptable one? What considerations should go into a design of a quarantine facility or methods? You would have to have quarantine facilities on the surface as well as perhaps on Earth. So how do you design into those? What are the special regions? Are there places where there's water, for instance, potential water, or where we're thinking we might find microbial life? Do you keep the astronauts out? And our previous talk talked about how you can do telerobotics to go in there very cleanly. What about questions for in situ resource utilization? If there are microbes in the ices, do you really want to have the astronauts drinking them? What's an acceptable containment for waste that you're going to leave behind? You won't bring everything back, and if they're human wastes and human-associated materials, then they will have microbes. And what will vent from any of the habitats or labs or suits that we have? And finally, natural transport. This is one that actually at SETI Institute, a researcher who was doing work on aeolian transport of dust, never occurred to her that she would be potentially helping planetary protection. But we need to know how do things spread. So you can take something that is a completely separate discipline, never before thinking about microbes, and now you put them together, and she's got herself some interesting proposals that could go into planetary protection research funding. So we've got all sorts of modeling about windblown dust, the probability of transporting hardy microbes, microbes that we know can live under extreme conditions, what will leak and vent out of the containers or the suits. What do we do for establishing those acceptable contamination generation rates and thresholds for the human landing sites? What about for the crewed systems and where they go? And how do we set acceptable contamination generation rates and thresholds for subsurface contamination? If you're going down into something that's a pristine subsurface aquifer, perhaps, or a brine area, are you going to be inserting things that are contaminated? So you've got to think about kind of sterilizing equipment that will be used robotically, but then dealing with keeping people away from it as a human space explorers. So combining them all together, you can see that there's an overlap. The red ones are the microbial contamination, and some of those things go into areas that are the areas of technology and operations. And if you look at the bottom one, the dispersal of microbes, well, that goes into everything from dispersal to microbes and dust and impact upon human health and also on technology. So we've got this process that's going forward, and it's a procedural instructions process, not a requirements process. And already we've gone through the first several steps. There's many more steps, but if you look at number 5, conducting studies and developing planetary protection requirements. Already one person who was listening to these telecons discussing things proposed the idea and asked the question, do we know what kind of microbes escape from the ISS? That resulted in the development of some sampling devices so that the astronauts could sample inside and outside the vents just to see what's there. So there's some very basic information that you can put together. So the conclusions, we do have an international obligation for planetary protection and responsible exploration. We know that forward contamination will occur, but it has to be controlled, and in order to do that, we have to understand it. Crew exposure to Mars material will occur. How do we tell if an astronaut is sick because of an immune problem versus exposure to a Martian something or other? So continued research, technology development and demonstration is what's needed here, and there's a lot of R&D opportunities to gauge the effectiveness of planetary protection controls, especially when we go to a place like Mars. So the report is just finished going through the ITAR and NASA reviews. It should be out very shortly, and the Planetary Protection website will have the executive summary probably within a week. So that's planetaryprotection.nasa.gov. And lots of questions ahead. Thank you.
All right. right. Well, thank you, everybody. We did start a few minutes late, and thank you to all the speakers for staying at or under your time. We got ourselves back on track, so we will not be the ones responsible if our headquarters friends are unable to start on time here. So thank you for that. Again, this specific session is broken by lunch. Okay, so we do have a couple more presentations in the afternoon. The topic is of interest to you, please come back to the room after your lunch. And then we will have time for discussion afterwards. Obviously, feel free to walk up to speakers and chat yourself. But again, make sure you come back and again, we'll have a discussion session at the end. Thank you.
We really did bring it back on time.
We did. I was worried there at the beginning.